All right, so how you guys doing today? Perfect. So make sure we have an exam week from today. Okay. So we'll finish up the chapter 15. We'll move on to the review session right away, so we can spend some time. We're also gonna hold another review session on Friday and also the other one on Monday. Okay. So let's. Okay. So we talked about the heterocycle. Well, you can say heterocyclic compound over here. So if you have any compounds that is in the ring structure than carbon, like a nitrogen, oxygen, sulfur, you can call them heterocyclic compound over here. Some of the heterocyclic compounds can be also aromatic. If you think about the one we talked before, okay, we have this one. So we have this compound. Pyridine compound over here. In here, this also can be aromatic. Just following 4n plus 2 Huckus rule done by German physicists. The way we're going to count those pi electrons will be over here 1, 2, 3, 4, 5, and 6. And then you guys wonder, what about this lone pair over here? That is actually the one in the sp2, which are same in here and here. In the your p orbital, the other potential pi orbital. So if you just exclude this lone pair here, it will be 1, 2, 3, 4, 5, 6. So that makes also one case of the Huckus rule will be 4 times 1 equal to 2 will be 6. So this will become our heterocyclic compound that is also aromatic because there's 6 pi electrons. Okay. So we also talked about the slightly different one. Okay. So we talked about the slightly different one. If we have this compound, okay, looks like this, okay, and then if we have a compound looks like this, in this case, we're gonna think the lone pair a little bit different in this time, because as you know, if you look at those, the already hybrid orbitals are in those 3 bonds or around nitrogen over here. In this case, we're actually going to count the ones, and the lone pair will be placed in p orbital. Okay? So that is why, even though you only see the electrons in the pi, electrons in the p, on this 2 double bond which is 4, and also those are the one can be also conjugated to those all the pi electrons in the p orbitals. So that will be make 6 still. Okay, so this is still aromatic too. Okay, in this case, the only difference we did from the other one was we actually count those 2 lone pair in the counting the pi electrons for aromaticity because now you have the bonds are all there, so there's the lone pair can be count for the numbers of pi electron for checking if it has aromaticity or not. Okay. So this is also we talked before. Okay. Makes sense, right? Good. Okay. So if that is the case, we have this almost same. Okay. This is what we call pyrimidine. Okay. So in this case, we have 2 nitrogen instead of 1 that we taught in pyridine. So we call this pyrimidine. We have 2 lone pair here, but same for those 2 nitrogen that one we taught in the pyridine. It has all in sp2, those over there. So you don't have to count those two lone pair in the aromatic city pi electron counting. So in this case, also it will be still 1, 2, 3, 4, 5, and 6. So it has 6 pi electrons. We can count for the aromatic city of the compounds. So this is also aromatic. So we have also another compound that looks like almost that. Over here. So we call this imidazole compound. So in this case, same here. This 3 bond over here. So we actually count the lone pair in this p orbital can be also counted in the pi orbitals in the ring structure with these 2 double bonds. But this one is here, here, here. So we in sp2. So we don't count this one, but this one. Okay. So that makes also 1, 2, 3, 4, 5, and 6. 5 and 6. So this one also has 6 pi electrons that satisfy one of the case of the Hooker's rule, which is 4 times 1 plus 2 will make 6. So this imidazole also become an aromatic compound, heteroaromatic compound. So we can try one more. Okay, let's try one more. I know it's a bit of tricky. But you can sometimes, we talked about the furan here before. But also we can try this one. This is the diaphragm. Okay. And then these two are also aromatic because you can count this one lone pair in the P, but the other will be in sp2 as well. So that will be P is sp2. So if you just count the numbers of pi electrons, you can do on those 1, 2, 3, 4, 5, 6. So it'll be 1, 2, 3, 4, and 5, 6. So these two are also good example of aromatic heterocyclic compounds. So the tricky part is if you need to count which lone pair in your aromatic city pi electron counting, then you can look up the bond and can see what you can do with this counting number here. I know this is kind of tricky, so let's try a bit of more practical problems. Okay. So technically we're done with the chapter 15. There's some other stuff, but won't be on the exam 1. So let me give you some example over here. So let's try this one. Okay. Let's try to review on this chapter first. Let's say what kind of a problem you may see on the exam. Okay. So if you can try to do this one. Okay. Here and here. Let me try to do it. Okay. So if you do this way, this is a bit weird. Let me double check. Let's try this one, okay? So if you try to do this compound over here, you can try to find out if this is aromatic or not. I'll give you about 2 minutes. You can try to count the pi electrons and see if you can go well with this Hooker's rule over here, okay? I'll give you about 1 or 2 minutes. Okay, 1 or 2 minutes. So try to count the pi electron in the compounds. So if I give this compound in your exam, you can tell if it's aromatic or not. Okay, try to. So maybe another minute and we'll do this together. Okay, so the let's try to count the pi electron over here. It'll be 1, 2, 3, 4, 5, and 6, 7, 8. Okay, so if it is 8, it cannot satisfy either 6 or 10 because the n can be only integers, including 0 here. So if you try 1, that makes 6. If you try 2, that makes 10, right? So then, but the numbers of the pi electron here is 8. So this will not be aromatic. Okay, makes sense, right? So let's try another one. If we have this one instead. This one. Let's try to do another 1 or 2 minutes and see if it's aromatic or not. I'll probably give you several numbers of compounds and I'll let you choose the one that is aromatic by just simply using Huckel's rule, which is 4n plus 2. So now we have a different compound. Another minute. Okay, try. Okay, so how many pi electron in here? Can you guys guess? It would be, yeah. Huh? 9? Oh, okay, so that's true. This is this is not perfect. So this is not aromatic, right? Perfect. But if I switch this one to here, how many? 10. Be 10, perfect. So, and then this will be aromatic. Actually, I drew this one wrong. I'm sorry. So this one will be aromatic. Because it's when you put 2 in n over here, that makes the 10 pi electron. So that is also a good example of an aromatic compound over there. Perfect. So that I think we have a really good understanding of the checking the aromaticity of the compound. I'll give you a little bit of tricky one. It's a little bit tricky. I hope you guys can get this one right, but don't worry about it. We'll try to do this together. Okay. So try to check the aromaticity of the compound over here. I'll give you about 1 or 2 minutes again. Try to find the pi electrons and try to account for the aromaticity of the compound. This is a bit tricky one, but we'll try this together. Okay, So what do you think? Do you think it's aromatic or not? Maybe, right? Yeah. So you can say aromatic. This is a tricky one because we do have 6 over here, but there's another one on here, right? So in this case, you don't count this because it's not inside the ring, ring structure. So technically, there is a 6 electrons in the p orbital, but those are the only ones that can be conjugate in the ring. So in this case, this is not aromatic. So this is a tricky one. So the thing is, you only need to count the pi electron in the carbon in the ring structure. That's the tricky part. So even though you see the electrons in 6 electrons in p orbital, you can try to conjugate, but the one you can actually use for conjugation is a 5. So it will not be aromatic. So it's kind of a tricky one. But kind of makes sense though, right? So one on the ring, that's the one you're going to count for the aromaticity. So that is tricky one. How about, can you guys try this one? This one. So now we have a charge. We have some cation molecules over here. And see if it's aromatic or not. So this is slightly different, but almost same rule anyway. This is slightly tricky, but you know, if you think there's a formal charge, consider there's no electron in P. That's pretty much the thing you need to know. Okay. So just 1 minute and we can do this too. Okay, so what do you think? It'll be aromatic or not? No, perfect. Good, because there is a p orbital here, but it's a covered cation, right? So it'll be empty. This is empty. There's nothing there. So only thing that you can count for the aromaticity in the pi electron will be only 4. So this is not aromatic. Okay, this is anti-aromatic. Okay, perfect. So let's do just one more. I think we can have a pretty good understanding now. So let's do one more and we can move on. Okay. So you can try to have this one. This is a bit tricky, but you can try to try. Okay, just try it together. So just tell me if it will be aromatic or not. Okay, that's it. About 1 minute or 2. This might be the most difficult one in this chapter 15. Okay. So the what do you think? This will be aromatic or not? Will be aromatic? Yeah? Okay, so this is aromatic. Good. Because there's 2 lone pair here. This one and this one will be in sp2. With those, you see those lines over there, right? Okay, so out of 1 out of 3. And then only the other lone pair on the sulfur will be counted as a pi electron. So it'll be so you ignore those 2, and there'll be 1, 2, 3, 4, 5, and 6. So that is okay with the Hakushu. Okay. Kind of makes sense, right? So this is something you can do with the ones that has a lone pair. You can try to count which lone pair will be counted for the pi electron for aromaticity. So you can double check. Okay. All right, so let's move on. Probably we're gonna do the review on Friday, on Monday. So hopefully we can have some another time for this one again. But I think we have some picture about how we're gonna do this arithmeticity of the compound. So now let's do the review, because we have some over here. Okay, so if you have, so the first chapter we did, the chapter 12 was mass spec. Okay, so if I give you the question like this, okay. Okay, if I give you this question over here, you need to choose the best answer. So when you do the mass spec, what might be the information you can get from the compound? This might be first problem you may see on the exam. So I'll give you different numbers of the spectroscopy we can use for like an NMR, mass spec, UVBs, and everything. But you need to find out like which spectroscopy will give us what type of information of the compound. So maybe, for example, if I give you mass spec, mass spectroscopy or metry, you're gonna choose which is the information that we get from the compound when you do mass spec metry. Okay, I'll give you about 1 or 2 minutes. Try to think about it. Okay, you can also think about what the other ones can be used. So it means it could be IR, it could be NMR, and the other way. Okay, but you just need to go ahead.
Can you read what those say?
Oh, this is this is the size and formula. This is the functional groups, and this is carbon and hydrogen framework. I promise I'll cut this in the exam. But, yeah. So the point is that if I give you a question like which spectroscopy or metry will be used for what type of information you will get. This is very good introductory problem you may see on the exam. 1 or 2 exams, exam problems. Okay, so let's do this together. So if I give you the mass spec over here, what kind of information you can get from those three will be the first one, okay? Because this is the mass spec is the one we're gonna find out the molecular weight, which technically means the size of the compounds. And by looking at the small fragment compounds that you can catch on the detector, you can possibly think about what might be the chemical formula of the composition there. So the mass spec is used for most likely the molecular weight, means size, and also some information about the formula. The functional groups, as we know, this is for IR, infrared spectroscopy. And then, as you also know, the carbon and hydrogen framework is what we use NMR. Okay. So either way is fine. So for example, if I give you IR in a spectroscopy, and I ask you what type of information you can get, you need to choose the second one, which is the functional groups. If I give you what might be the information you can get from NMR, you need to choose the carbon and hydrogen framework in the compound, either way. Okay? So you can predict what question you may see on the exam, the first part. Okay. Make sense, right? Good? Okay. All right, so since we talked about the mass spec, which is chapter 12, let's try to do some problem over here. So if I give you mass spec graph over here, I'll try to put this one, okay, and then I'll put it over there. This is a kind of a general pattern you see on the like a linear shape arcane structure here. And then I want you to find the parent peak, and our base peak. So just copy this one real quick and try to look for which one is our parent molecular ion peak or the base peak. Okay. It's pretty easy, right? So you just need to know which peaks are the one that stand out for the 100% abundance and the relative abundance, and the one that has tell you the actual molecular weight of the compound. That is what we're looking for, the parent peak and the base peak. Okay. Okay, so it's pretty easy, right? So which one is the parent peak? The molecular ion. Perfect. There's the far right one, right? So this is the what you can actually tell. Oh, this is the molecular weight of the compound easily from the mass spec spectrometry. What is the base peak? If it's 1, 2, 3. You put 3, right? Perfect. This is the base peak, which can be used for your 100%. So this is a relative term. So you have a most abundant fragment number over here, and that is the tallest peak. You can see we consider them as base peak because this will be your 100%, and the other one we measure how many percent based on this base peak. So we call this base peak. That's why. Okay. Make sense, right? Good. Okay, perfect. So another one. Can try. Oh yeah. So we have we learn about this one here. Whenever your organic compounds goes in, you're going to experience certain type of electron bombardment on the compound. So when they break apart, they're going to break apart. So when they break apart, when we can, this one over here. Okay, so you're going to find so this is the cation, because this is also radical, because it was done by electron bombardment. So high energy electron hit this one really fast, and then it makes this compound lose the electron because of the electron push them each other. So you have a radical form because it lost the one electron, and also positive charge because also lose electron over here. So when they break apart in the fragment, you're going to have the radical ones, and the one that has the positive charge is cation. But it's always going to be the one that has more substitute with this R carbon here will be the one that carries the positive charge, and this is the peak you're going to find in the mass spec, because when you do when you're detecting the fragments, you're gonna use the magnetic field that makes the curve on the motion of the compound fragments, and the one with the charge can be the only one that can curve. This one will not, because it doesn't have any charge here in radical form, so we'll just hit the wall of the mass spec. So this is the only thing you're gonna find on the data and the peak. So keep this in your mind, okay? For this, the problem we're gonna do over here. Okay. Makes sense, right? So try to, and this one is the positive charge because it's more stable. You guys remember carbocation stability, right? So instead of doing this one, so there's just two scenarios. This could be radical, this could be cation, right? Either way, but this will not be happening because this will be very unstable. That is why you're gonna get this one is positive charge, and this is the one you're gonna find in the graph. So this will be not shown on the graph. Okay. Okay. So let's try to keep this in your mind. This is the reason why. This is how you can solve the problem like this one. So if you have, I'll give you two compounds. So the one will be looks like this. Okay. The other one will be looks like this. Okay? So if you try to calculate for the chemical formula, will be the same. Meaning you're going to have a same number for what? Molecular ion or parent peak over there. So you have 1, 2, 3, 4, 5, 6, 7, right? So 7 carbon. Can you guys guess how many hydrogen will be there? By looking at the structure, will be 14. You don't have to do the calculation because this is just the ring structure over here, right? So that makes the, if it's linear, it could have been what? C7H16, because it's a CnH2n plus 2. But because of this ring structure, well, you lose a pair of hydrogen to make the ring structure. So they will be same as CnH2n whenever you have a ring structure with all single bond. So if you count the carbon there, you automatically know, oh, there will be 14 hydrogen. You don't even have to count it. You can also do double check by just doing this, right? Let's try to count the here. Okay. You can always double check, right? So it'd be 3, 4, 5, 6, 7, 8, 9, 10, 14. Yeah. But you don't have to do this. I think you just know by just looking at the structure easily, okay? So this is the same. There'll be 7 and 14 hydrogen. So molecular ion peak wise, we cannot distinguish these two. But if you remember this, what we just discussed like 5 minutes ago, we know the most abundant peak, which is most quite stable, will be this one. For this one, will be this one. Okay. This is where you can find your base peak, because this is quite stable fragments. You're gonna find which will be most abundant in your graph. So this is most likely your base peak. For this one, you're not gonna find a lot of this one, but this, okay? So this is the this one. Okay? So this will be your base peak, most likely. Okay? When you do the electron bombardment to make it fragments. Because the one that has in this carbon is more stable with the other 2 carbons here, but those ones only have 1 carbon to each other, or just hydrogen here. So even though you're gonna see the same number for the molecular ion peak or the parent peak, you're gonna see the different numbers for the base peak. So when you look for that base peak, you can identify which compound that is for that graph. Only thing you have to do is this one is what? The one carbon is 12, 3 hydrogen is 3. So you're gonna lose a 15. Your total compound molecular weight minus 15. So if you do this one over here, which is the 7 carbons, which is 12 times 7, which is what? 84, right? 84. And 1 hydrogen is about 1, so it'll be 14. So it'll be 98. Okay? So it'll be 98. So you're gonna have these two will have the same parent peak as around like a 98, right? This is the same in chemical formula. But the base peak wise, this one will have this one, which is the 19 minus 15. So this is the base peak on this one with methyl cyclohexane will be 19 minus 15 will be 83. Okay, so it will be base peak over here for this one. For this one, okay. But if you have this one, in case you're gonna have a base peak on where? So you're gonna have you're gonna cut here, right? So which is CH3, CH2. CH3, CH2. So the 2 carbon is 24. there'll be 5 hydrogen in the radical form, which is 5. So it'll be 29. So same number from the parent peak, but 98 minus 29 will be what? Will be 69, right? Am I right? 69? Okay. So in this case, your base peak will be in 69. Because of the carbocation stability, in this case, this is more frequently happening. If they cut over here, that is the way they can find the most abundant fragments with the more stable in carbocation form. And this one is a slightly 1 carbon less ring structure, which is here. So they will lose 29, they will lose 15 to get to their base peak. So if I give you the peak like this, you need to choose, this is the answer. Okay? Makes sense, right? Let's do one more. Let's do, if I give you, so for example, if I give you this one, okay, and then this one, okay, so there'll be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So in this case, they're all same in chemical formula, right? And then only structurally different. If I give you these two instead of the other two we talk, the graph you just need to look at is here, same. Only thing you have to change is you understand they need to have this, and this will be very abundant. That's the only thing you have to know to get the most abundant stable cation form, carbocation form on these two. So it'll be this one, right? And this one. Yeah, this one, okay? So they break apart with the one methyl group like radical form will be break apart, and this is a ethyl group like and radical form will break apart from there to make more abundant stable form of the thing. Then if I give you the peak, so if you count for this one, there's 8 carbon over there in the one green structure, so it's a 16, right? So in this case, 8 times 12 is what? 96, right? And plus 16, right? Because 1 times 16 is 16. That makes what? It's 112, right? 112. 112 over here. Okay. So they will have a same parent peak, which will not be able to distinguish these two by looking at this one, but the base peak will do it because they do have this one will lose 29, this will lose 15. So if I give you some base peak on like 97, what's the compound between these two? With this one, cycloheptane. Makes sense, right? Does it make sense? So this is, so if I change this one to, so 29 over here, right? This will be 3. So if you have base peak on 83 instead of 97, it will be this one is answer. Because this will lose the 29 to be the base peak, which is this one. Okay, we good? All right. So I'll just stop here today.